Good morning, my math minions. How are you doing today? Or I guess it could be afternoon, evening, night, for some of us. Who knows what kind of schedule we're keeping right now. But today, we're jumping right into the topic of quadratic functions, all right? Now, we got a couple things that we want to be able to do today. First off, we want to be able to look at equations or tables or graphs and be able to just identify, based on just looking at it, whether it's a quadratic function or not. So we need those key characteristics. We're going to be able to write quadratic functions to model real-world scenarios. So we want to be able to write those equations based off of information we're given. We want to be able to identify the vertex of a quadratic function. So you kind of have an idea what a vertex is, so we'll see what that means for a quadratic function. And then we're going to write the quadratic functions in standard form and intercept form. And those are going to help us when we get to graphing later on. So, first off, we've been dancing around this idea of quadratic functions every time we've been factoring in the past where we've had an x squared equation. That's a quadratic function. All right, I should say expression. But anyway, here's the idea. If the degree is 2, that means it's quadratic. All right, it comes from some Latin quadros, which means squared. And so we've got that 2 in there, I believe. So anyway, the parent function that we typically look at when we think about it in function format is f of x equals x squared. That's the most simple and basic type. And then later on, we're going to do some transformations and stuff, move it around where we push it up and down, left and right, all that jazz. All right, now what does standard form mean? Standard form is like the standard form of a polynomial. We want the quadratic function, we want the terms that are written in order in decreasing degree, right? So we've got a 2, this is an exponent of 1, and this is like an exponent of 0 because there is no x. It's like x to the 0, right? Anything raised to the 0 power is a 1, so we don't even need to worry about that part there. So they're in decreasing order, and then it goes from 2 to 1 to the constant if you have one. What does intercept form look like? Intercept form is when a quadratic function is written as y equals x minus p times x minus q. You look at that, I don't see anything squared. But if we take this first term times this first term, which is what those parentheses are telling us, right? If we do our double distribution, we know you're going to get x squared out of that. So it's going to be a quadratic. And here's the cool part. The p value and the q values, those are going to be the x-intercepts. So if you know what it is, if they say x minus 4 and x minus 2, you'll be able to figure out, oh, that crosses at 4 and it crosses at 2 on the x-axis. It'll help us when we graph and do some other things with it. Another vocabulary term, parabola. We've talked about parabola in class, I'm sure. A parabola is the graph of a quadratic function, and it makes a U for the most part, okay? It looks like a U, although it's going to keep getting wider and wider as it goes up. And then the last vocabulary here, we've got the vertex of a parabola. The vertex of a parabola, it's kind of hard to describe, but basically it's this. It's the maximum or the minimum of a parabola. It's the highest or the lowest point, right? It just depends. Do we have a U? Do we have a U that's shaped up like this? Well, then the vertex is going to be that spot right there, and that's the lowest point, okay? And if we have the U shaped down, right, pointing down, then that's your vertex, which makes it the highest part. So you can't just say, oh, it's the highest or it's the lowest. It just depends on which direction the parabola is going. All right, here we go. Quadratic functions are different from linear and exponential functions, right? Linear and exponential functions are always increasing or decreasing, just depends on which way they're pointing, for the entire domain, right? They're always going up. The y values are always getting bigger or always getting smaller. It doesn't change direction. But quadratic functions do, right? Quadratic functions switch directions. We've seen this before when we talked about absolute value functions. You can look at the graphs below. We've got the absolute value function right here. Okay, here's my absolute value function, right? And here's my quadratic function. And if you notice, let's talk about some of those things, right? They both change direction. See, the absolute value function, it comes down like this, hits the bottom point, and shoots back off, right? Same thing with a quadratic, although it's a little bit smoother, more curved than straight, and we still have those arrows on the end, all right? So it looks like they both have a low point in the parent function, right? And don't forget that all of these could be flip-flopped, right? They could be reflected and have a high point instead of a low point. What else do I notice? Well, those branches, right? They keep getting wider. They're going farther to the right and farther to the left on the absolute value. Same thing on quadratic. Now it's curving up, but it's getting wider as it goes. All right? It's getting wider as it goes up and down. So they have a low value. Part of the graph, when we're on the negative side, when x is negative, let's say this, if x is less than 0, it's decreasing, right? For all my values that are less than 0, right? So if I split my graph in half, right, I'm going to just split it in half right there on the axis. Everything over here, if I look at this point right here, let me change colors so it'll make it a little easier for it. If I look at this point right here, and then this point, and then this point, they're all getting smaller. Same thing with the quadratic. It's getting smaller and smaller, okay? But as I go to the right, when x is greater than 0, it's increasing, right? So that's what I mean by it switches direction. When it changes it, right, it's going up. Both of these do, right? They're going up as I move to the right past 0, okay? So why do we think that is? When I look at this, just looking at it in general, both the quadratic and the absolute value, all my y values, all the y values are positive. I'm just talking about the y values. It's above the x-axis. I don't have anything down in here, right? They're all above. Why do we think that is? Got to think a little bit here. When you do the absolute value, that's what it does, right? An absolute value makes the number, changes the number positive because the absolute value is defined as the distance on a number line from 0. So whether I move left or right, it still has a distance, and typically in math we think distances as positive. So absolute values, all right, absolute values make values positive. So what is it about the quadratic? What is it about squaring a number? Well, that's the same thing. When you square a number, you square any real number, it's going to be positive. It will always be positive because a positive times a positive, you pick any number, the number is either going to be positive or it's going to be negative. If you pick a number and it's a positive number, a positive times a positive times a positive will always give you a positive value. And likewise, if you pick a number and that value is negative, a negative times a negative will also be positive. So similar to absolute value, if you square something, it's going to make it positive, okay? Now, that's when we just have the basic case, y equals x squared. When we get crazy stuff like we see below in example 1, it might be positive, it might be negative, it can move up and down and shift and do transformations. We'll get to all that later, okay? I don't want you to think it's always going to be positive later on, based on what we add and subtract to it. It could move up and down that axis. All right, here we go. Quadratic functions have a degree of 2, but sometimes they can be tricksters. Let's figure out which one of these are quadratic. This one, easy, quadratic. It's got the degree of 2 right there. This one, easy, quadratic. It's got the degree of 2, okay? There's nothing higher, all right? It's not in standard form, but it's quadratic. If I want it in standard form, I just have to flip-flop that around, x squared plus 2x. Letter C, that's a negative 2. That's not quadratic, no. And letter D, I better put yes since I didn't circle it. Maybe we'll circle the whole thing. Letter D, this is what we're talking about. If I needed to, I could multiply this out. Remember, y equals x times x is x squared. X times 1 is 1x. Negative 1x. And negative 1 times 1 is a negative 1. Those cancel in the middle. Y equals x squared minus 1. Yes, that's quadratic. All right, so 3 of those are. If it has the highest degree, if the highest exponent is 2, it's going to be quadratic. All right, let's keep going. This is going to be a little bit tough, so stick with me here, all right? There's nothing difficult about what we're doing, but just the idea of it. How do you look at a table, right? Because we just looked at, let me go back here and make a point. We go back here. We know that it's from an equation is quadratic because it's x squared. How can I look at a table? Oh, sorry about that. How can I look at a table and determine whether it's quadratic? And this is actually really easy. But you got to have kind of an idea. There's a pattern that shows up. So let me show you the pattern before I tell you what it does. First thing we need to know is, what does it mean to find the first difference? Well, the first difference is when you take your y values and you're going to do y sub 2 minus y sub 1. What does that mean? You're going to take the second y and subtract the first y from it. So what I'm doing is here, I'm going to start with this 1 right here. I'm going to say 1, the y where I'm at, I'm going to take this one right here, and I'm going to subtract this one. y2 minus y1. So that's going to be 1 minus 0, 1 minus 0, which is going to give me 1, right? And then I'm going to do 4 minus 1, 4 minus 1, which is going to give me 3. And then I'm going to do 9 minus 4, 9 minus 4, which is going to give me 5, and 16 minus 9 is going to give me 7, and 25 minus 16 is going to give me 9, and 36 minus 25 is 11. Now here's the deal. I already know, let me erase all this work right here. I already know that this is going to be quadratic because I can recognize in this part right here, those are all my perfect squares. 0 squared is 0, 1 squared is 1, 2 squared is 4, 3 squared is 9, so on and so forth, right? But check out the pattern that just formed, right? You got this 1, 3, 5, 7, 9, 11. That's kind of neat. If I think about that pattern, it's going up by every odd number, right? The first one went up by 1, and then the second went up by 3, and then 5, and then 7. But to prove that it's going to be a quadratic, check out this. You take the second difference. So we're going to do what we just did. But you're going to take the first differences, okay, the first differences, and we're going to do y sub 2 minus y sub 1 on that, right? Basically, in this case, I'm going to take 3 minus 1. I'm going to take the line I'm on, subtract the line above it. 3 minus 1 is 2. 5 minus 3 is 2. 7 minus 5 is 2. What do you notice is happening here? 9 minus 7 is 2, and 11 minus 9 is also 2. If your second differences are all the same value, if you have a common second difference, you will have a quadratic function. Let me say that again. If you have a common second difference, you will have a quadratic relationship. All right? And so if you remember back to the beginning of the year, to find if something is linear, you want a common first difference. A common difference is all we called it. But now we have second differences. So a common difference gives you a linear equation. But if that's not common, right, we see these aren't the same right here, then a common second difference can give you a quadratic. Let me show you how that works over on this second example. Does the following table show a quadratic relationship? If we do 4.5 minus 2, we get 2.5. If I do 8 minus 4.5, I get 3.5. If I do 12.5 minus 8, I get 4.5. And 18 minus 12.5 is 5.5. And then if I subtract each of those from each other to get the second difference, see, difference means subtraction. I subtracted the first column, now I'm subtracting the next one. I get 1, 1, and 1. Those are all the same, so the answer is yes, this is quadratic. Later, we're going to use this idea to show arithmetic, geometric, and quadratic sequences, so keep this check in the back of your mind. But if you have a table, that's how you find out if it's quadratic. Do a second difference, all right? Let's quickly get through these last couple examples. All right, now we want to be able to look at a graph and see if it's a parabola, okay? And so what do graphs and parabolas look like? They're going to be U-shaped graphs. All right, sketch the graphs of parabolas with the following information, then list the domain or range. Okay. The minimum, this is a parabola with a minimum at 1, negative 2. So I'm going to go right 1, down 2. That's my minimum value, all right? And if it's a parabola, it's going to look like this. It's going to be a U shape going up like this, okay? That's all I know. I don't know how wide it is. I don't know how quickly it rises. It might be narrower. I could have the same type of graph. Let me do this in blue. Maybe it's a lot narrower, right? So it's rising quicker. Or maybe it's something that's going a little bit wider and it's a U shape like this. But here's some ideas. When you draw your parabolas, make sure they're symmetric, okay? This is something we'll learn later. It's got an axis of symmetry, so anything on one side is going to be equal to something on the other side, okay? But of all these parabolas, here's the great part. All these parabolas, all three of the ones I just drew there, they all are going to have a domain that is all real numbers, okay? Because it continues to move to the right and to the left, and it's continuous, meaning it's all connected. So all real numbers for all of my domains. If there's no other information, your domain is going to be all real numbers, right? Now the range. For the range, I'm talking about all the values. Here's my low point right here, okay? You see this -2 on the y? That's my low point. When I talk about the range, I'm talking about my y values. All my parabolas are pointing up, right? So they start at -2 and they're going up here. So I'm just saying my range is going to be y is greater than or equal to -2. Whatever the y value is of your minimum or maximum, the vertex, if you will, that's going to be the clue for your range. All right, let's try another one. Maximum at -3, 1, 2, 3, up 4, 1, 2, 3, 4. There's my maximum. If it's a maximum, that means that it's pointed down like this. Okay, there we go. Pretty standard parabola there. Again, domain, all real numbers. Remember that. The domain is all real numbers. The range, we're pointing down this time. Here's my high value. So I'm going to grab the 4 from the vertex. Y is less than or equal to 4 because it's pointed down. Here we have a vertex at 2, 2. Vertex at 2, 2. 1, 2, 1, 2. 2, 2. That's the ballerina's point. Get it? 2, 2. All right. It opens down. So again, looks like this. Going like that. Again, this is getting wider and wider and wider. It will eventually, the farther out we go, hit every real number on the x from left to right. But on the range, we got to grab the y value there. It's pointing down, so we're going to say y is less than or equal to 2. That's what a graph of a parabola looks like. It's a U shape, and it's going to have that maximum or minimum. We call that the vertex. Last one here. A packaging company makes rectangular bubble mailing envelopes. The length of the envelope is always 2 inches more than the width. The length is 2 inches more than the width, all right? Now, that means we want to do everything in terms of the width, a sub w, right? We want to write a function that models the area of the envelope based on the width. We know this. Area equals length times width because we have a rectangular bubble mailing envelope. We also know that the length is equal to 2 inches more than the width. So I have to take the width and add 2. So now, to get the area based on the width, I'm going to substitute. Instead of using L in my equation, I'm going to use W plus 2. And instead of using, well, no, I'll just use the W, right? So it's basically going to be W plus 2, that's my length, times W. I want to leave it in intercept form. Why is this intercept form? Well, because this is kind of like this. Check this out. Intercept form, we know intercept form would look like W minus P times W minus Q. We saw that earlier in the notes. So in this case, how is that intercept form? Well, what we have is W minus -2, and we have W minus 0, right? Because adding is the same as subtracting the negative, right? Anyway, A sub W, or A of W, is equal to W plus 2 times W minus 0. All right. What are the roots, the x-intercepts of the function? The x-intercepts are going to be, check this out, you have one of your x-intercepts at 0, that comes from this part right here. The other x-intercept comes from this W plus 2, and we got to change the sign. So we've got an x-intercept at 0, and we have an x-intercept at -2. Now, sometimes we want to write those as an ordered pair, 0, 0, and -2, 0. Now, rewrite your function in standard form. So in standard form, we got to flip this in, right, like that. A of w is equal to w squared plus 2w. The y-intercept comes from the constant. There is no constant. It's like we're adding 0, right? So the y-intercept is at 0, 0, which we saw from the roots, the x-intercept. If the domain of the function is 3, 4, 5, and 9, okay, the domain is the x values usually, but in this case the domain would be your w values. So it's saying if I have a width of 3, a width of 4, 5, and 9, what is the range? So if we're talking about these envelopes, that means that they only make envelopes that are 3 inches wide, 4 inches wide, 5 inches wide, and 9 inches wide. So then the question becomes, what are the lengths of envelopes that they do? So if it's a 3-inch envelope, we can take that 3 and plug it in. We'll say A of 3, which is going to give me 3 squared plus 2 times 3, and that's going to be 9 plus 6, which is 15. So when I find my range, it's going to be starting at 15, okay? If I plug in 4, let me do the work here. 4 squared is 16, 2 times 4 is 8. So we have 16 plus 8, which is going to be 24. Wait a minute. This isn't making any sense. Okay. Oh, that's right, because this is the area, not the length. Gotcha. Cool. We're good. Take the 5, plug it in. We've got 25 plus 10 is 35. Sorry. Took a little second there. And take the 9 and plug it in. 9 squared is 81. 2 times 9 is 18. 81 plus 18 is going to give me 99. In this range, remember, I was thinking about it incorrectly. I was thinking that it was the length. Those are not the length values. Those are the areas, right? If the width is 3, then the area would be 15. If the width is 4, the area is 24. If the width is 5, the area is 35. And if the width is 9, the area is 99. Okay? So that's our introduction to quadratic functions. There's a lot going on there. You'll get to practice that a little bit in class. And hopefully this all makes sense to you. And you can jump on to the practice worksheet or do some of the other stuff to get a better handle on it. So let's just review the goals real quick again. We want to go here. We wanted to identify quadratic functions from equations, tables, and graphs. If it's an equation, we know it's going to have x squared for the degree. If it's a table, we look at the second differences. They have to be constant. And if it's a graph, we're looking for the U shape. We modeled it in the real-life scenario with the envelopes. We identified the vertex of a quadratic function. That's the low or high point. We did that on the graph. And we wrote it in standard form and in intercept form. We did that in the envelope problem. Okay? All right. Hope that helps. Put this on double speed, hopefully, and it'll go a little bit quicker for you. Have a great day.